In this video, I will explain how to make substitutions in integrals. I will work with indefinite integrals. Making substitutions in definite integrals is very similar and requires one additional step of adjusting the limits of integration, but that step is usually very simple. Let's begin by looking at the notation we use for integrals. When we would like to write an integral, we begin by writing the integral sign, then the function that we're integrating, let's say f of x, and then at the end of the integral we put dx. Have you ever thought about why do we need to put dx at the end of every integral? Why not just use the integral sign and the function that we're integrating? And the integral sign will tell us to integrate the function that follows the integral sign. There are many reasons for including dx at the end of each integral. One of these reasons has to do with Riemann sums being used to define definite integrals. In this video we will concentrate on a different reason, and that reason has to do with making substitutions. Suppose we were not using dx at the end of an integral, so if we look at the following simple example, the integral of 2x dx equals, you probably know that it equals to x squared plus an arbitrary constant, right? This is just saying that the antiderivative of 2x equals x squared plus a constant. Suppose we were not using dx at the end of the integral sign, then our formula would look as follows: integral 2x equals x squared plus c. Now, suppose we want to make a substitution in these equations. Suppose we want to substitute, let's say, instead of x, t squared. So I would like to substitute instead of x, t squared in these formulas. Let me first do it on the right hand side, where the integral notation for the integral does not include dx at the end. We proceed to replace x with t squared everywhere we see it. And so that gives us integral of 2t squared equals t squared squared plus c. And if I simplify the right hand side, then we get that the integral of 2t squared equals to t to the fourth plus a constant of integration c. Now note that this result is actually incorrect. The antiderivative of 2t squared is not t to the fourth, because if we take the derivative of t to the fourth, this derivative would equal to 4t cubed and not 2t squared. So there is something wrong going on here, and the dx at the end of the integral is something that corrects what goes wrong here. Now let's make that substitution x equals to t squared on the left hand side, where I'm using dx, including dx in the notation for the integral. So on the left hand side we would get integral of 2 times t squared. I'm substituting instead of x t squared. But now, since the integral includes that term dx, we also need to include d of t squared. And really this is a multiplication. So after the integral sign, what we have is 2 times t squared times d of t squared. On the right hand side we'll have t squared squared plus c. Now, what is d of t squared? So this is where we would need to know what that actually is. And first I'm going to give this a name. So dx is the differential of x. And likewise, d of any function of x or of t of any other variable is defined to be the derivative of that function multiplied by the differential of the variable on which the function depends. If the function is f of x, then its differential would be the derivative of that function multiplied by dx. Now, in our case, we need to calculate the differential of t squared. And so the differential of t squared is equal to the derivative of t squared multiplied by dt. And the derivative of t squared is 2t. And therefore the differential of t squared equals to 2t multiplied by dt. And so this is what we will put into our integral instead of d of t squared, the differential of t squared. And then the left-hand side of our integral will be rewritten as 2 times t squared multiplied by 2 dt. And this is going to be on the right-hand side, of course, this the right-hand side simplifies again to t to the fourth plus c. And if we multiply 2t squared and 2t under the integral sign on the left-hand side, we will get final result, namely that the integral of 4t cubed dt equals to t to the fourth plus c. And now you see this is the correct result because if you differentiate t to the fourth, we obtain 4t cubed. And therefore t to the fourth plus an arbitrary constant is indeed the correct antiderivative of 4t cubed. So let's summarize. One of the reasons we include a term such as dx at the end of each integral is that that term is actually a really useful device that helps us to make substitutions in integrals, in formulas that can include integrals, and we obtain correct results if we take an equation, a correct equation for an integral, and then substitute instead of x, or whatever the variable in the integral is, something else, another expression, or another function. To obtain the general formula for the integration by substitution rule, let's begin with an integral of a function of the variable u. So let's say we have an integral of some function f of u du. And let's follow the process that I just explained to substitute instead of u some function of another variable x. So let's substitute instead of u another function g of x. Now, at first, this process is completely mechanical. We go into the integral of f of u du, and everywhere we see u, we replace it with g of x. And so what we get is integral of f of g of x times the differential of g of x. And now we need to calculate the differential of g of x. So let's just remember that this differential is equal to the derivative of this function, g prime of x, multiplied by the differential of x. And so if we put that into our integral, we will get integral of f of g of x times g prime of x dx. Let me rewrite this formula in its final form from right to left. And so I would like to take the right hand side of this equality, integral of f of g of x times g prime of x dx equals to the integral of f of u du, where u is equal to g of x. This is the general formula for the integration by substitution for indefinite integrals. Let's see how this formula is applied in practice to calculate integrals. So here's an example. Suppose we need to calculate integral of 2x square root of 1 minus x squared dx. Okay, so looking at this integral, the first thing that you will notice is that what makes this integral rather complicated is the square root of 1 minus x squared. We can't really simplify the square root of 1 minus x squared. Algebraically, there is no way to rewrite it in the simpler form. But we can try to make it look simpler by introducing another variable. So suppose we set 1 minus x squared equal to u. And the reason we may want to do that is that now, instead of square root of 1 minus x squared, we will have, it will now look like square root of u. It will now be square root of u, and we can rewrite that even further as u to the power 1/2. So that simplifies that part of the integral that contains the square root. And moreover, if you calculate du, the differential of u, it is the differential of 1 minus x squared. And we can calculate that as the derivative of 1 minus x squared multiplied by dx, which is negative 2x dx. Now, if you look at our integral that we need to calculate, right? So the square root of 1 minus x squared, that became square root of u, and the next term, 2x, let's combine it also with dx. So we're looking now at 2x dx. That's the term that we have in our integral in addition to the square root. So 2x times dx, that's almost du. Not quite, but almost. In fact, the only thing that we need to change in this expression, negative 2x dx, is we need to get rid of the negative sign. So let's go ahead and solve for 2x dx. It's very easy. To solve for 2x dx, we just need to multiply both sides of this equality by negative 1. And so what we find is that 2x dx is negative du. Now we can put all of this in our integral. So we have integral of 2x square root of 1 minus x squared dx. And we're making the substitution u equals to 1 minus x squared. And the square root of 1 minus x squared becomes square root of u. And then instead of 2x dx, we will put negative du. Okay, well now the integral got simplified substantially, and it is actually not difficult to complete the integration. Let's rewrite the square root of u as u to the power 1/2. We have a negative sign. We can actually factor it out of the entire integral. And so we get negative integral of u to the power 1/2 du, and we can now complete this integration by using the power rule. Increase the exponent by 1, divide by the new exponent, add the constant of integration. Now simplify the answer. It gets simplified to 2/3 u to the power 3/2 plus c. And at this point, we want to go back to the original variable, because our answer so far is in terms of u, but if you look at the original integral, there was no u in it. And so we do want to get our answer to be in terms of x. Going back to the original variable x is very simple. Here, all we need to do is substitute instead of u 1 minus x squared. So let's go ahead and substitute that. And that gives us our final answer, negative 2/3 times 1 minus x squared raised to the power 3/2 plus a constant of integration c. So to summarize this process, really you could see here that what helped us to calculate this integral was the fact that one part of the integral, namely the square root of 1 minus x squared, this could be simplified by introducing a new variable, 1 minus x squared equals u. But what's really is allowing us to make that substitution and simplify the integral is the fact that the derivative of 1 minus x squared also appears in our integral. Namely, the derivative of 1 minus x squared is negative 2x. We don't have negative 2x in our integral, but we have positive 2x. And so this is what this general formula that I wrote earlier refers to, where you have under the integral sign, you have the function f of g of x, and then times g prime of x dx. So one part of your integral can be expressed in terms of some function of x, and then the other part of this integral has something to do with the derivative of that function. These are the circumstances in which you can successfully make a substitution. Let's now take a look at a very similar example. Suppose we need to integrate 2 times square root of 1 minus x squared dx. This integral is very similar to the integral that we just calculated. Both contain 2 square root of 1 minus x squared. The first integral has an additional term of x, which is lacking in the second integral. By quickly looking at these two integrals and comparing them, you might think that the second integral is simpler because the function under the integral sign contains fewer terms. However, as we will see, now the second example integral is much more complicated. First, it's reasonable to try using the same substitution as we used in the previous example. Let's try to substitute u equals 1 minus x squared. The one reason using this substitution is reasonable is because if we substitute u equals 1 minus x squared, then the square root of 1 minus x squared becomes simply square root of u. And so this substitution does simplify one of the terms in the integral. However, in order to complete this substitution, we need to express all terms in the integral, including the differential dx term, in terms of u. As earlier, du equals to negative 2x times dx, but additional calculations will now be needed because we cannot simply solve for 2x dx as we did before and use that to complete the substitution. That is because the x term is no longer present in our integral. So, therefore, to complete the substitution, we need to first solve this relation du equal to negative 2x dx. We need to solve this relation for dx. Dx equals to negative du divided by 2x. And then we need to express x in terms of u. Right? Again, we can go back to the equation that relates u and x. U equals to 1 minus x squared. And we can solve for x, expressing x in terms of u. First, we will get that x squared equals to 1 minus u. And then taking the square root, we find that x equals to square root of 1 minus u. Now, this has to go into our formula for dx. So we had an expression for dx. Dx equals to negative du divided by 2x. And now we express x in terms of u, and we obtain that x equals to square root of 1 minus u. And now we can substitute square root of 1 minus u for x in this expression for dx. So then what we get is dx equals negative du divided by 2 times square root of 1 minus u. Okay, so at this point we can complete our substitution, and I will rewrite the integral. So we started with the integral of 2 times square root of 1 minus x squared dx. And now we're substituting u equals to 1 minus x squared. And we found that if that is the case, then dx relates to du according to this equation. Dx equals to negative du over 2 times square root of 1 minus u. And so when we go ahead and plug this into our integral, as we said earlier, square root of 1 minus x squared now becomes square root of u. And then instead of dx, we need to plug in negative du over 2 times square root of 1 minus u. Here, the only cancellation, the only simplifications we can make is we can cancel 2 in the numerator and 2 in the denominator. We could also pull out the negative sign out of the integral. And so what we get is negative integral of square root of u du divided by square root of 1 minus u. Let's take a look at this result. What we see is that even though one of the terms in the integral got simplified, the rest became more complicated. That is essentially because expressing dx in terms of du resulted in us having to put an additional square root in the denominator. Comparing the two integrals, you will probably agree that the second integral that we just obtained in terms of u is not simpler than the first. And so this substitution doesn't really help to calculate this integral. So how can we then calculate this integral? Integral of 2 times square root of 1 minus x squared dx. One of the difficulty of integrating this function is that it contains the square root of 1 minus x squared that cannot be simplified algebraically the way it is written. Now, if we can substitute instead of x something so that 1 minus x squared becomes a complete square, then the square root will go away. If you think about different functions, different expressions that we could substitute instead of x, it is not so easy to see what needs to be substituted to turn 1 minus x squared into a square. However, if you happen to think about trigonometric functions, you may realize that if you substitute instead of x sine function or cosine function, then that would actually turn 1 minus x squared into a square. Let's see how that happens. So let's go ahead and substitute instead of x sine, let's say, of t, where t is our new variable. The first part of making this substitution is completely mechanical. We go into our integral, and everywhere we see x, we replace x with sine of t. And so we get integral of 2 times square root of 1 minus sine squared t times the differential of sine t. And this is where you will begin seeing why this substitution is potentially a good idea. By the familiar trigonometric identity, 1 minus sine squared t is equal to cosine squared t. So now what we have under the square root is cosine squared t. Let's also calculate the differential of sine t right here. The derivative of sine t equals to cosine t. And so the differential of sine t will equal to cosine t multiplied by dt. Now, let's assume for simplicity that cosine of t is positive. Then the square root of cosine squared t is just cosine t. I have to be a little bit careful here because if cosine of t takes negative values, then the square root of cosine squared of t will be negative cosine of t. However, you could check that in both cases, cosine t being positive and cosine t being negative, the end result after we integrate, after we make a substitution, integrate, and then return to x, the end result is the same. And so actually it wouldn't matter in the end whether cosine t is positive or negative. So assuming that cosine t is positive, then we can simplify square root of cosine squared t as just cosine of t. And so our integral turns into integral of 2 cosine t times cosine t dt. In other words, integral of 2 times cosine squared t dt. We did achieve some simplification of our integral because our original integral contained the square root, and after the substitution the square root went away. So we got rid of the square root. However, we paid a price for the simplification. Now we have trigonometric functions in our integral, and on top of that, cosine of t is squared. The next step is to use another trigonometric identity. The double angle formula for cosine says the following: cosine of 2t equals 2 cosine squared t minus 1. And from here, we can find that 2 cosine squared t equals cosine of 2t plus 1. And therefore, we can rewrite our integral as the integral of 1 plus cosine of 2t, all of that times dt. The rest is fairly simple. First, distribute dt and split the integral into two integrals. Integral of dt plus integral of cosine of 2t dt. The first integral is immediate. Basically, we're integrating 1, and the antiderivative of 1 as a function of t is just t. Integration sign and d sign cancel out each other. We get t. For the second integral, we can make a substitution. And let's set 2t equal to u. Then du would equal to 2 times dt. In other words, if we solve this for dt, dt will equal to 1/2 du. And so we can rewrite the second integral as the integral in terms of u, cosine of u times 1/2 du. 1/2 as a constant can be pulled outside of the integral, and then we can easily integrate. The antiderivative of cosine u is sine u, and so we get t plus sine u plus c. Of course, I need to replace u with what it is in terms of t. T plus sine of 2t plus c. And now we need to go back to our original variable, which was x. We will need the relationship between x and t. Now, if we go back to where we made our substitution, the substitution that we made was x equal to sine t. So Let's look at that. Solving this equation for t, we find that t equals to arc sine inverse of x. So that's going to go into our final result instead of t. We also need to express sine of 2t in terms of x. Now here there is one way to do that would be to again use a double angle formula from trigonometry, this time for sine. Sine of 2t equals to 2 sine of t times cosine of t. And sine of t, that's our x. I think I lost the constant here. I apologize. So this 1/2 right here, when we pull it outside of the integral, it should have been present here. So it should be 1/2 sine u and 1/2 of sine of 2t. And so really we should be rewriting 1/2 of sine of 2t in terms of x. 1/2 and 2 cancel out. Sine t becomes x. And then cosine of t, if you think about what cosine t is, we can actually use the same trigonometric identity that we used at the very start, namely cosine equals square root of 1 minus sine squared x. Or t, I'm sorry. But sine t is x, and so that becomes square root of 1 minus x squared. Putting all of this together, we find that 1/2 of sine of 2t equals 2x times square root of 1 minus x squared. And so our final answer is, I'm looking at the answer in terms of t, and now we're expressing everything in that answer in terms of x, and what we find is t is arc sine x, and then 1/2 of sine of 2t, that is actually x times square root of 1 minus x squared, and then of course we need to add our constant of integration c. So that's how we can calculate this integral. And the two examples, example 1 and example 2, show two different ways in which integration by substitution can be performed. In the second example, we actually substituted a function for x. So it's kind of like a direct substitution where you find an appropriate function to replace x with. In the first example, we let a portion of a certain part of our integral equal to the new variable, and then the rest of the integral was expressed in terms of that variable or its derivative. And so these are the two different ways in which you can use integration by parts.